Thank you. I thank the organizers for preparing this conference of our society, which is nominally the 9th, but actually the 10th, since there was also a virtual one in 2020. And I'm one of the persons who were present at each of them. And this presentation is based on my recent work, currently under review, and it's a natural extension of an earlier work done together with Tomasz Trześniewski and Lukiewski. I'll start with outlining the broad context and motivation for this research. Then, in the first part, I'll discuss the kinematical algebras, first at the classical level, and then the concepts of quantum deformations and quantum contractions, without trying not to go too much into technical details. While in the second part, I will sketch the landscape of deformations of these Lorentzian and Non-Lorentzian kinematical algebras. Again, not showing all the formulae, which would be impossible to digest, but rather illustrating this landscape with a few diagrams and saying a few words about the special cases. I will finalize with a short summary. This study contributes to the exploration of symmetries, which, as you all know, are a cornerstone of physics. And more specifically, I restrict here to symmetries of various kinds of spacetime or space-time. The kinematical algebras, such as Poincaré, Carroll, or Galilei, as well as their central extensions, such as Bargman algebra. Then the algebras of asymptotic symmetries, such as the famous BMS and its extensions, which have also been recently generalized, the Carrollian and Galilean counterparts. Then, in the context of quantum gravity, and especially quantum gravity phenomenology, that is the approach not to formulate the complete theory of quantum gravity, but the approach in which we are trying to find some testable predictions, not really predictions, some possible signals which could be of quantum gravitational origin. We consider deformations, quantum deformations of both kinds of symmetries, formulated in the language of Hopf algebras and related structures such as the bialgebras. And this has also been quite recently generalized to these deformations of BMS. What I'm concentrating on in this presentation are Carrollian and Galilean versions of Non-Lorentzian kinematical algebras. And why to consider 2 plus 1 dimensions? So obviously, 3 dimensions, as always, can serve as a testing ground for various concepts. And moreover, in this case, we already have a complete classification of possible deformations described in the language of algebras. In this work, I examined the contractions relating deformations in the cases of vanishing and non-vanishing cosmological constant. And moreover, in 2 plus 1 dimensions, these deformations arise actually naturally already at the classical level, at least in the Chern-Simons formulation of 3D gravity. Now, before moving on to kinematical algebras in 2 plus 1 dimensions, let me so briefly outline the growing relevance of Carrollian and Galilean symmetries in general. I mean, among these kinematical, the algebras that I mentioned, we have this, which I call Lorentzian, that is Poincaré, de Sitter and anti-de Sitter. We have the Carrollian versions, Galilean versions, as well as other, so far, less explored and maybe a bit less interesting cases, which I will not discuss here. But Carrollian symmetries arise in 2 distinct ways. Firstly, when we consider the limit of speed of light going to 0, so-called ultra-relativistic limit. In such a case, free particles as well as strings turn out to have trivial dynamics, so they do not move. And hence this limit can also be called ultra-local. It can also be studied in GR, and then it turns out that there are 2 different versions of this Carrollian limit, called electric and magnetic. And an expansioner of the Carrollian limit turns out to be related to the stronger expansion, to the Bielinski-Kalatnikov-Lifshitz conjecture for space-time singularities, asymptotic silence scenario, and other things. Secondly, Carrollian symmetries are actually symmetries of a null hypersurface in a Lorentzian manifold 1 dimension higher. And in this context, they have been applied in the study of black hole horizons, as well as planar gravitational waves. And it also turns out that BMS group, which describes symmetries of asymptotic null infinity, is actually a conformal extension of Carroll group 1 dimension lower. Galilean symmetries can be seen and actually can be mathematically described in a certain sense to be dual to the Carrollian symmetries, and not just the symmetries but also over associated structures. And they are better known. They arise in the non-relativistic limit, that is actually the limit of Galilean relativity, of speed of light going to infinity. And because of that, they are associated with a weak gravity expansion. And they appear in the study of gravitational waves, for example. And there are also, for example, applications of these symmetries, these mathematical and mathematical structures associated with them in other areas of holography and string theory. Now, turning to the case of 2 plus 1 dimensions. Here, Poincaré and the Sitter and anti-de Sitter algebras can be expressed in a unified fashion, for example, like that. And in order to arrive at the Carrollian versions of these algebras, we need to rescale the boost generators as well as the time translation generators by C, and then take C to 0. The resulting algebra is characterized by vanishing bracket between generators and boosts, as well as between generators and boosts and time translation, which reflects the fact that Carrollian boosts act only in time. This corresponds to what I said before, that particles, at least free particles, on the Carrollian manifold cannot move, they only evolve in time. Conversely, for the Galilean the counterparts of these algebras, we rescale again boost generators, but now by c to -1, and time spatial translation generators, and take the limit of c going to infinity. The resulting algebra has again the vanishing bracket of boost generators, as well as boost and spatial translation generators, and in special translations also commute between themselves. And this reflects the fact that Galilean translations act only in space. These are Galilean boosts act only in space. Galilean symmetries, obviously, are symmetries of classical mechanics. Now, I also need to stress, and this is actually what I use, that the Carrollian versions of de Sitter and anti-de Sitter are isomorphic to Euclidean and Poincaré algebra respectively, at least at the mathematical level, but when we consider overstructures, these are non-equivalent constructions. But yeah, here I just present the brackets for the Euclidean algebra in the sense of the Euclidean counterpart Poincaré, and show this well-known isomorphism between de Sitter-Carroll and Euclidean algebra and anti-de Sitter-Carroll and Poincaré algebra. And also I should mention that the Galilean versions of these algebras, de Sitter and anti-de Sitter, are also known by the names of expanding oscillating Newton-Cook algebras, as well as some other names less commonly used. And now moving to deformations. I will not introduce the whole mathematical machinery here, but just give you a broad overview, a very broad overview. So instead of breaking of symmetries, which is also sometimes considered in exploration in the search for possible quantum gravity, we may consider deformations. And an example that can be given, the best studied example actually, is the Kappa-Poincaré algebra, which in 2+1 dimensions differs from these brackets I showed before, just by the right-hand sides of these two brackets of commutators of boost generators and boost and special translation generators, as well as certain extra structures that I will mention on the next slide. And spacetime, which is covariant with respect to such deformed symmetries, is non-commutative. So non-commutative geometry is related to this deformed, quantum deformed algebras, or sometimes called briefly quantum groups and quantum algebras. And there's also this other approach to non-commutative geometry, which is spectral non-commutative geometry, and there's certain partial overlap between these two approaches. But here, the crucial structure is this deformed algebra of symmetries. And again, just to show you an example for this Poincaré algebra, the non-commutativity is of this form that time coordinates and spatial coordinates are non-commuting, while spatial coordinates commute between themselves. And the deformation parameter kappa, which appears also here and here and here, is what controls this deformation. And the classical limit is recovered for kappa going to infinity, which can very easily be seen here. When this right-hand side simply vanishes, here we only minus J0 is left, and here P0 times this chronicle delta. And these extra structures that I mentioned here are the structures of a Hopf algebra. That is, when we are deforming a Lie algebra, or this also applies to all other kinds of algebras, but in this context, the Lie algebra, we actually need to generalize it to the structure which is known as a Hopf algebra, which is equipped not just with a Lie bracket, but also these two other maps, which are called coproduct and the antidot, which one coproduct goes from the given algebra to the tensor product of its two copies. So in the opposite direction as the product, and the antidot goes from the algebra to the algebra. And actually, this has already been mentioned on Monday in the talk by Andrea Levi. And in the discussed example of Poincaré algebra, the non-trivial coproducts and antipodes are of this form. And in the classical limit of kappa going to infinity, all of them recover this trivial form, which is here. Now, if a deformation is a so-called coboundary deformation, the situation in the study of these deformations is simplified by the fact that it can be characterized by an object which is called a classical R matrix. So when we have this coproduct structure, it can be expanded with respect to deformation parameters, because in general there can be more than just one deformation parameter. And in the first order is determined by this object, which is called the classical R matrix, which is an element of a tensor product, or in this case anti-symmetrized tensor product of two copies of the algebra. And more precisely, we need to consider an equivalence class of such objects, because by applying automorphisms, we are not actually changing our deformation to a different one. And this object, this classical R matrix, is also equivalently defined as a solution of this equation, which is known as the classical Yang-Vector equation, and is expressed in terms of a generalization of the Lie bracket for since R is an object, is an element of a tensor product, but this is actually exclusively expressed in terms of just ordinary Lie bracket. And on the right hand side we have an invariant of the algebra. And now a crucial tool in the exploration of both Lorentzian and non-Lorentzian deformations of both Lorentzian and non-Lorentzian algebras is the method of quantum contractions. This method, in contrast to ordinary contractions, what I mean by ordinary contractions, when we have the algebra and we perform these rescalings and take the limit, this is contraction of the algebras. Similarly, when we start with the Sitter or anti-de Sitter algebra, and you may have this cosmological constant hidden in the generators, and we first need to rescale, and then take the limit to recover Poincaré algebra. So this is just a procedure of taking the limit for the algebras. And for deformations of the algebras, kinematical algebras in particular, we have to again slightly generalize this method. This generalization consists in rescaling also these deformation parameters so that the limit is well defined in a given case. And in general, for these deformations in 2 plus 1 dimensions, we vary scaling depending on the kind of contraction that we consider may require a rescaled by a given parameter by the square of let's say C, or in some cases you don't need to rescale a given parameter. There are some technical details with which I will not worry too much, and namely, sometimes we need to redefine the parameters before rescaling, so that we can obtain the most general result. On the other hand, some parameters after the contraction can be eliminated by suitable automorphism. And also another subtlety is that in some cases, by applying an automorphism and then a contraction, we can obtain a result which is inequivalent. That is, in this, let's say, we have these 2 versions of the same R matrix, which differ just by an automorphism. So they describe the same deformation for this anti-de Sitter algebra, but when we perform the Carrollian contraction, it turns out that these 2 R matrices characterizing 2 deformations are no longer equivalent, since simply this automorphism, which was relating these 2 deformations, is not inherited by the algebra after the contraction. And this also happens for the Sitter-Galilei. And one more way in which the results are simplified is that there can be some trivial contributions to the deformation. And this happens in particular for Galilei and Sitter-Galilei algebras. While in other cases, the number of terms and hence the structure of the deformation is simplified after the contraction. Maybe I need to speed up a bit. So, as I mentioned, some deformations, for some algebras, deformations can be characterized by these objects called classical R matrices. And for semi-simple and homogeneous pseudo-orthogonal algebras, the examples of which are well-known Poincaré, Euclidean, de Sitter, anti-de Sitter, as well as de Sitter-Carroll and de Sitter-Carroll. All possible deformations are characterized by these classical R matrices, so it suffices to study these classical R matrices in order to obtain the complete classification of all deformations. And then, when we consider these quantum contractions, we recover these classifications up to some missing terms, but in some classes, but it allows us to conjecture that in the other cases for Galilei, Carroll, de Sitter-Galilei, and de Sitter-Galilei, for which not all deformations, for which we don't have the full classification, but I just studied these contractions, it's possible, and it's just a conjecture, that these contractions allow us to recover almost all possible deformations. And now, as I said at the beginning, showing you all possible formulae that I obtained in these papers would be impossible to digest. Therefore, I just present these figures. So this is for Poincaré, the Sitter, and the Sitter. Each R is one R matrix, and this equivalence class and corresponding to a given deformation. And they are connected, they are related by these quantum contractions. And in some cases, we first need to apply automorphism, as I said before performing the contraction, in order to arrive at independent results. Yes. In the case of Carroll and Galilei algebras, we obtain, I obtain only these deformations which can be derived as contractional limits. So possibly there also exist some additional ones, as well as there exist deformations which are not characterized by R matrices. And in the case of Sitter-Carroll and Sitter-Carroll, we have this isomorphism which I mentioned at the beginning with Poincaré and Euclidean algebras, and this allows us to immediately obtain the complete classifications for them, just using this already known full classification for Poincaré and Euclidean algebras. And then we can study the quantum contractions. As I already said, we recover all these deformations up to a few missing terms. While for Galilean algebras, I only considered these deformations which can be obtained by contractions, but possibly there exist some additional ones. And as I discuss in more detail in my paper, it's interesting to trace what happens with some of the special cases of deformations, especially the ones that have been studied in various contexts in detail. And what happens with them reflects the nature of Carrollian and Galilean regimes. That is the fact that in the Carrollian regime we have absolutization of space, that is, we have this ultra-locality, while in the Galilean limit we have absolute time. So when there is a deformation in the timeline direction, for Galilean algebras it basically vanishes, while for the deformation in the space-like direction it doesn't vanish, but it's made in a sense milder. There are some terms which drop. And another interesting case is of the deformation is related to the so-called dreamful double construction. So now I should finalize. So this is just a summary of what I've already said. That in this paper, actually it's two papers, I extended the classification of deformed ABS and Poincaré algebras to the ABS-Carroll algebras, and then showed that we recover almost all deformations of these algebras and Poincaré and Sitter-Carroll by studying the quantum contractions, approximately lambda going to 0 and c going to 0. And that and I showed that what deformations we can obtain from Carroll and Sitter-Galilei by these quantum contractions, and how special cases behave. And here I also again stress why the case of 2-12 one dimensions is worth to be considered. Okay, maybe I will start here.
We have time for one or two questions.
So at some point you mentioned that this Carrollian symmetries will be somehow related to elliptical issues. So could you say something more on this? How it's related to this hypothesis?
That is, as far as I know, and this has been described in a very recent papers, just 1-2 years old, when they were studying the expansion around the Carrollian limit of the general theory of relativity. They observed that it's very similar to gravity, to an expansion with respect to the gravitational constant, and it seems to be related to the decay of conjecture, but this is something that still needs to be explored.
Just two very short questions. First one, I mean, is this a complete classification or classification with certain assumptions? I mean, because you focus on kappa deformation, but I mean, does it include this the classification of all deformation includes all possible IQ deformations or all that?
The classification is complete in the sense of all possible Hopf algebras are classified in the cases of Poincaré, the Sitter and the Sitter, as well as the Sitter-Carroll and the Sitter-Carroll.
So it includes like Q deformation as well?
Yeah, the 2 + 1 dimensional counterpart of the Q deformation. And there are no extra assumptions.
Okay.
Just that we consider coboundary deformations.
So
the ones that are characterized by classical
classical deformation. Okay. And the second question was the problem with 3+, so higher dimensions. I mean, Lorentz or Poincaré, there's been deformations that have been classified by Carrollian.
No, but Carrollian said that actually there are some deformations that are still missed in this classification. But yeah, it's a natural next step, obviously, to explore. And some special cases have already been explored by Ballesteros and his collaborators in particular.
So let us thank the speaker here.